Are you guys able to see my screen? Okay. So in the last class, we talked about machine learning, supervised learning, unsupervised learning. We talked about decision trees. We talked about something called information theory, entropy, and also information gain. And we saw an example of if our given data set is this table, how we can calculate the entropy. In this example, the entropy of wind was calculated for us. We saw details about that in the last class. In the very beginning of today's class, I want us to calculate the entropy for output, decision, comma output. This isn't, the calculation isn't given in the slides, so let's try to do it together to get a better idea how we can calculate entropy in general. If you're not clear about the idea of entropy, I would just to watch the previous lecture. I give the link in the classroom. So after watching that, I hope you'll be a bit more clear what entropy is. But in short, entropy means impurity. We are trying to calculate entropy so we can use that value later on to calculate information gain. And by calculating information gain, we can determine how we can design our decision tree, which nodes we should pick as the root and the next one, and so on. Okay, so let's to calculate the entropy for outlook. We need first the entropy of our decision. So how can we calculate the entropy of decision? If we go to this slide, it gives us the equation for calculating entropy. So let's try and follow that. The equation is the probability of yes times log base 2 probability of yes. Minus probability of no times log base 2 probability of no. In this case, if we go back to the table, we see that we have to calculate how many yeses are there and how many no's are there. So let's calculate the no's in row 1, row 2, so 1, 2, 3, 4, 5. There are 5 no's, and since there are 14 datas, so 14 minus 5, that's 9 yeses. So our probability of yes should be 9 divided by 14 times log base 2, 9 divided by 14. Yes. We have 5 nodes, so the probability of no should be 5 divided by 14 times log 2, 5 divided by 14. Now, if you add that in a calculator, you should get something like this. Something like 0.94. So this is the entropy of decision. Now, what are we trying to do? We are trying to calculate the way they calculated the gain of decision comma win. We will be trying to calculate the gain decision comma out, output. So first we have to see how many possible values are there for output. Are you guys following along? If you have any questions, feel free to interrupt. So first let's look at how many possible values are there for outlook. There's sunny, there's overcast, there's rain, and that's it. So there are three possible different values for output: sunny, overcast, and rain. We have to calculate the entropy for each. Mm, sure. Okay, first let's calculate it for sunny. This decision, no, decision while outlook equals sunny. So, how many sunnies are there? One, two, three, four, five. So, the equation would be same. The equation for entropy. So, I'll just copy that and paste it here. So, the probability of yes. So, there are total 5 sunnies. One, two, three, four, five. And among them, how many are yes? We see 1 and 2 are no. We see number 8 is no. Number 11 and 2 yeses. So in total there are 5, 3 no's and 2 yeses. So first the step in, so it should be 3 divided by 5 times 2, 3 divided by 5. Starts with the minus and also there's a minus at the middle. 2 divided by 5. I'm doing this for this is the probability of no. 2 divided by 5 means log base 2, 2 divided by 5. Let me put that in a calculator and see the value. When you're putting it in the calculator, remember this is a log base 2. If you're using just log, that would be base 10, so you will not get the right answer for that. If you have a calculator nearby, I would suggest you try it with me, just for practice. So if you put this in a calculator, wait, I forgot to put 2 here. Yeah, now it looks good. If you put this in a calculator, you will get 970 something, 09, something like this. So let's take 3 digits. I'll take 1 here. So 0.971. This is the entropy of decision while outlook is equal to sunny. Similarly, we have to do this for all the other possibilities. Outlook can be overcast and rain. So let's do it for overcast and rain. Change this to overcast. Okay, for overcast, first one is one, two, three, four. For overcasts, the first one is a yes, second one is also an yes, third and fourth, all of them are yes. Collectively yes. There are four possible overcast outlooks, and all of them are yes. So the probability should be four are four, out of four there are four yeses. Four times four divided by four. Yes. And how many are for no? There is zero for no. So it's four divided by zero divided by four. That's two. Zero divided by four. If you put this in a calculator, should get a actually you should get an error because the calculator will say this is invalid for a log. So since 0 divided by 4 is 0 and anything times 0 is also 0, so when you see that there's 0 divided by something, you can also forget about this part. You can assume that the entire thing will be 0. And in fact, if you put this in a calculator, this should be 1 and this should be 1. So 2 to the power 0 should be 1. So this value should also be 0. You can test it out in a calculator if you want. So the entire thing is going to be a 0. And finally, let's do for rain or rain. So there are one, two, three. That's almost trying to find. Again, if you feel like I'm going too fast or you're not understanding something, feel free to interrupt. Okay, now we're trying to calculate the entropy of decision while outlook is equal to rain. So how many are possible rains in our data sets? Let's see, 1, 2, 3, 4, 5. So the first one is a yes, the second one is a yes, and the third one is a no. The fourth one is a yes, and the last one is a no. So there are 3 yeses and 2 nos. I'll check that again. 1, 2, yes. 2, yes. So 3 yeses and 2 nos. So what's the probability of yes? Should be 3 divided by 5 times log base 2. 3 divided by 5. There are 2 no's, so the probability of no should be 2 divided by 5. Because there are 5 rows for output equal to range. Log 2, 2 divided by 5. Alright, so if you put that in a calculator, it's going to give you 0.971. Okay, now that we have the entropies of all the possible outlooks, we can calculate the information gain. How can we calculate the information gain? Let's see the slide again. In the slide, it was done for wind. So there were two possible values for wind, weak and strong. So they're calculating the entropy for weak, just like we did for outlook sunny, overcast, and rain. And next, they calculated the entropy for decision while wind is equal to strong. After that, here is where they calculated the gain. So the equation of gain is you have to use the value of entropy of decision minus the probability of decision while wind is equal to V times the entropy of decision while wind is equal to V minus wind is equal to strong, wind is equal to strong. So we get the idea what we have to do. We're trying to calculate gain decision, comma, output. The first thing we have to do is use the value of entropy of decision, which is 0.940. So to subtract that from, first we have to calculate the probability of decision while outlook equals to sunny. So how can we do that? We go back to our table. So here we see sunny. There are 1, 2, 3, 4, 5. There are 5 possible sunnies out of 14. So the probability of decision while at outlook equal to sunny should be 5 divided by 14. Because out of 14 rows, there are 5 sunnies. Times the entropy of decision while outlook equals to sunny. We calculated that right here. So this should be 0.971 minus the probability of decision while outlook equals to overcast. If we look at the table again, you'll see that there are 4 possible overcasts. So this should be 4 divided by 14 times, actually it's times 0, so it doesn't matter. And the last one is outlook equal to rain. So there are 5 possible rain outlooks. So it should be 5 divided by 14 times, and we calculate the entropy for decision while outlook equals rain. 0.971. Now, if we put that in the calculator, 0.949. If you have a calculator nearby, you can try it with me. So the value I get is 0.246. So we calculated the gain for while decision, comma outlook. Let's check the slide if we got it right. So the the gain of decision, comma outlook. So 0.246 seems to be correct. So did we understand how we can calculate the information gain, how we can calculate the entropy? Can we do it on our own from now on? Well, the calculations might look a bit too complicated, but I'm sure with a bit of practice, everyone of you guys can do it. And if you do face any difficulties, you can always reach out to me. Okay, fine. We calculated the gain of decision, comma outlook. So now what happens? Similarly, we have to calculate the decision, comma temperature and the decision, comma humidity. We have to calculate um, the gain for all the attributes available: outlook, temperature, humidity, wind. After calculating all the information gain of each attribute, we have to compare them and decide that which one we should take as the first root node of our tree. So the more information gain, that means the more efficient it would be if we choose it as a root node. So by comparing all the information gains, we see that 0.246 is the largest. So taking outlook as a root node would be the best choice for us. So we are starting to draw a tree. This is our root node. There are three possible values for outlook: sunny, overcast, and rain. So far we just drew one node, a root node. Now we have to try and complete the tree. So there are three possible values for outlook: sunny, overcast, and rain. We have to decide what should happen when outlook is equal to sunny, when outlook is equal to overcast, when outlook is equal to rain. In the next slide, if we see that we're trying to figure out what should be the decision if outlook is equal to overcast. When we see outlook is equal to overcast, we see that all of the decisions are yes. In our training dataset, all the decisions of outlook equal to overcast is yes. That means we can come to the conclusion that in our root node, if outlook is equal to overcast, we can automatically come to a decision, and that decision is yes. But things are not so simple for when outlook is equal to sunny or outlook is equal to rainy. When outlook is equal to sunny, we have to calculate the information gain, just like we did in a few minutes ago. For all the other possible attributes, we have to calculate when gain outlook equals sunny. That means this is our given table, and we have to calculate it for temperature, humidity, and wind, because these are the remaining attributes. So this time we have to assume that this is our entire table, because right now we are here. After outlook is equal to sunny, we have to find a decision, find the decision or another node. So we have to assume this is our table, and then we have to repeat the process of calculating entropy and information gain. So if we're trying to calculate the information gain of temperature, first we have to calculate the entropy of temperature equals hot, then temperature equals mild, and temperature equals cool, because these are all the possible values of temperature. After calculating all these entropies, we can use the formula to calculate the information gain of temperature. Similarly, we would have to do all that for humidity and also for wind. So since I showed you the entire process, I'm hoping you will be able to do this by yourself. And there's also examples in the slides. So I would suggest you try this on your own. The values are given in the slide, and match the values to determine if you did it right or wrong. So if you're done calculating the information gain of outlook equals sunny, while temperature and humidity and wind, hopefully you'll get these values. And after that, you'll have to decide again that which information gain is maximum. And taking that will give you the most efficient trade. So in this particular case, we see that humidity is the right decision because it has the highest score of information gain when outlook is sunny. That means uh, when outlook is equal to sunny, we should put another node here, and that should be humidity. Are you following along? If you have any questions, again, feel free to interrupt. And then we have to check the values. At this point, if we see that if humidity were high, then we see the decision is in all cases the decision is no. And if humidity was normal, the decision was yes. And again, this is for outlook equals sunny. So when outlook is equal to sunny and humidity is high, the decision is most certainly no in all cases. And if outlook is equal to sunny and the humidity is normal, then the decision is yes in all cases. So then we after outlook is equal to sunny, we add a node here called humidity, and then if humidity is equal to high, we can come to the decision no, and if humidity is equal to normal, we can come to the decision yes. Let's quickly peek at the final decision trees just to get an idea. So outlook, if it's sunny, then humidity, and if humidity is equal to high, we come to the decision no, And if humidity is equal to normal, then we come to the decision yes. All the leaf nodes must be final decision. Yes or no? So we haven't done the right side yet. Let's see how that came to existence. So we talked about the possibility of outlook being overcast and outlook being sunny. So the remaining one is outlook being rain. If outlook is rain, then we have to calculate the entropies and the information gain again for all of them. And after that, we can see that the highest wind will produce the highest value. So then we have to choose wind. So for outlook equals rain and wind equals weak, we see that the decision is always yes, and for outlook equals rain and wind equals strong, the decision is always no. So on the right side of outlook, if outlook is equal to rain, we should come to the conclusion that there should be another node, wind, and depending on its value, if it's strong, then our decision should be no, and if it's weak, our decision should be yes. So we see that all the leaf nodes have actual decisions, yes or no, then we can say that this is a complete decision tree. So even though we had in the table, using only those three attributes, outlook, humidity, and wind, I think, we were able to come to a decision every time. So this is the most efficient decision tree we could come up with using this algorithm. So this is the entire process of how we can come up with a given data set. Any questions so far? All right, so moving on. So the next part says that there can be extensions of the decision tree algorithm. The thing is, in the algorithm we followed, it's called ID3, and there's an issue with this algorithm. The thing is, if we have a lot of one-sided data, that means, let's say, in our um, in our table, we see that there are a few sunnies for outlook. There are a few sunnies, few rains, and a few overcasts. But if we had one-sided data, biased data, let's say out of 14, um, 12 or 13 were sunny, one was rain, and the other one was overcast. If we have data like that, our decision might be a little overfitted, and so we have the proportion is very different for sunny, rain, and overcast. If one particular data is dominant in such a vast term, then our training data might not be very fitting. And the way we use to calculate the information gain, the entropy, we're not really taking any ratios. We're rather calculating all the values. So this problem will lead us to a biased decision tree if the data is a bit unbalanced. So to improve that, there's an extension of ID3 which is called C4.5, which uses the gain ratio instead of the information gain. In the very first point, you see, using gain ratios. If we use ratios or percentages, that would be much more accurate, and that would save us from the trouble of biasness or unbalance because we're taking ratios now. So how can we use gain ratios instead of information gain? In the next slide, we see an equation for calculating gain ratio right here. We see that the gain ratio should be the gain divided by split info. So we already know how to calculate the gain or the information gain. Now we have to know what is this thing called split info. In the next slide, there's an example given how we can calculate these things. This time, the table says that there are one, two, three, four attributes called age, income, student, and credit rating. And our decision is buys a computer. Buys computer, yes or no. That's the decision. So based on age, income, student, and credit rating, we have to determine if the person will buy a computer or no. So at the very beginning, we have to calculate the entropy of the decision, which is buys computer or buys computer. So there are okay, so out of 14, there are 5 no's and 9 yeses. So you see this line info D, this is basically calculating the entropy. So this is the probability of yes, 9 out of 14, log base 2, 9 by 14, minus the probability of no, which is 5 by 14, times log 2, 5 by 14. So it's 0.94 is the entropy of Bayes computer. Now we have to calculate the entropy for age, income, student, credit, all of them, and then finally calculate the gain. So if we're done calculating the gain, we should see these values. So now the question was, we already know how to calculate the gain after calculating the entropy and everything, but the question was, what is split info? So after calculating the gain, you'll get these values. The gain of income should be this, the gain of student should be this, the gain of rating should be this. So on the next slide, it says that how we can calculate the split info. It says here that this is the split info of income. So where did these numbers come from? Let's go back. Look at income. There are three possible values for income: high, medium, and low. So how many are high? One, two, three, four. There are four highs. Medium one, two, three, four, five, six. Six mediums and five, four. Four lows. So the first portion is high. The second portion is medium, and the third portion is low. It's very similar to calculating entropy. So the probability of high should be 4 divided by 14 because there are 14 total rows, and out of them 4 are high, times log 2, 4 by 14, minus 6 by 14 because there are 6 mediums of out of 14. So the probability of medium should be 6 divided by 14 times log 2, 6 divided by 14, minus 4 divided by 14. This is 4 for low income. 4 divided by 14 times log 2, 4 divided by 14. So to calculate the split info, we have to um, use this equation to calculate all possible values. The probability times log 2 probability. So is that clear how we can calculate split info? For example, if we're trying to calculate the split info of, let's say, student, we have to see how many possible values are there. There are no and yes. So, how many no's are there? One, two, three, four, five, six, seven. Seven no's, and one, two, three, four, five, six, seven. Seven yes. So, the split info should be minus 7 divided by 14, which is the probability of yes, times log 2, 7 divided by 14, minus 7 divided by 14, which is again no, the probability of no, times log 2, 7 divided by 14. So, any questions, how, or confusions, or you still didn't understand how we can calculate the split info? So, after calculating the gain for each attribute, we can calculate the split info for each attribute, and then we have to calculate the gain ratio. In the slide, the gain ratio for income is given, which is basically the information gain divided by the split info. So the information gain was 0.029, and the split info is 1.557. So if we put that in the equation, we get the ratio. And this time we'll be looking at the ratio instead of the information. So the attribute that has the maximum gain ratio will be selecting that one as the root node, and so on, the next node, and so on. So, any questions, or if you guys are following along? So that's pretty much it for decision trees. Um, let's look at the next slide. So it's saying what I said just now. So you should choose the maximum gain. The ID tree algorithm uses the maximum gain method to selecting the best attributes. And instead of lesser values and most values, if we use the gain ratio, that would be more balanced. And in the next slide, it says measuring the model quality. So after you're done creating a model, in this case, the decision tree, we need to um, we need to calculate the accuracy, how well the model performs. So how good is the model? We have to predictive. We have to calculate the predictive accuracy. We have to see the false positives and the false negatives. We have to try and minimize the loss for overfitting. Okay, what are false positives and false negatives? These are practically when your model is saying that something is true, but it's actually not true, that it got wrong. When it was when it was supposed to predict and it got a wrong value. So when it falsely predicts something is positive, it's called false positive, and when it falsely predicts negative, it's false negative. And also we have to keep in mind of the training error. And we have to keep in mind that we're not subject to overfitting. What overfitting means is that if we're using training data, and our training data is something that is, let's say, if we use, how can I get an example of overfitting? Um, let's say we used some kind of data that some values, we're not using a lot of data, but the training data set, some values are pretty much fixed and it didn't change much in our training data set. For example, if we didn't have, let's say, most of our outlook was overcast and all the overcasts were yes. If we didn't have, let's say, sunny or rain, let's say all our training data set was outlook equals overcast and all the decisions were yes. If we used that as a training data set, that would be called overfitting because when we actually try to predict a real life scenario where the outlook is sunny or rainy, it will always give the decision yes because all it knows is outlook equals to overcast and that's yes. It wouldn't be able to predict anything other than that correctly. All it knows is if outlook values something, it should be yes. So that's called overfitting. Your training data should have variations as much as possible. So we should try and avoid overfitting. We should carefully select our training data if we want to build an accurate model. That's very important. The final point is regularization, attempt to avoid overfitting, just what I said. And the thing is, there's a trade-off. Um, the more complex you try to build your model, the less simplistic it will be. So there's always a trade-off. If you want to keep your model simple, the chances are it will be less accurate, but it will be a simple model. You'll be able to reuse it. You'll be able to understand it quite simply. But it will be less accurate. So, but if you, a better example would be this. Sorry, this one. So, let's say if your data sets are like this, so if you choose D, something like D, that's pretty much a straight line. So this is choosing simplicity over accuracy. We are willing to let go of a few data samples because we want to keep our algorithm simple. And on the other hand, choosing something like C would be making sure that all the data are properly aligned, but uh, our algorithm or our model can get a bit complex. So that's trading off simplicity for accuracy. So that's completely up to you or whoever is making the model, which approach you should choose. If you want to keep it simple, you have to keep in mind that the trade-off will be you will get a less accurate model. But if you are willing to go to that level of complexity, the trade-off will be you'll lose the simplicity. Your model will be a bit complex, but your accuracy should be better. So the next slide tells us something about cross-validation. So in general, what cross-validation means is that using multiple different algorithms to create different models and comparing between them to validate which one is performing better for your case. So let's say you have a problem. You should use multiple machine learning algorithms. You can use different classifications or regression algorithms and then compare them. They compare the accuracy, compare compare the predictions, and then come to a conclusion that for your training data set, that this algorithm was more accurate than that one. This is the basic idea of cross validation. You're trying to validate within multiple machine learning algorithms. So one of them is called holdout cross validation. Uh, what it says is that we should divide data into training sets and test sets. What that means is that let's say you have let's say you have 1,000 rows of data. What holdout process validation means that you shouldn't use all the data to train. You should split the data and create a training set and a test set. The training set is for training, and to measure the error set, we have to use the test set. So let's say if you have 1,000 rows of data, you can split that. Let's say you're using 800 to train your model, and then the remaining 200 to test your model. Then you can get an accuracy of if your model was successfully able to predict the remaining 200 correctly. So that's a good approach. In the convention is to split it around 70% to 70-30 or 80-20. So for if you let's say if you have 1,000 rows of data, you can use 700 of them to train or 800 of them to train, and the remaining should be used for testing. So a question arises that if we're always, let's say for 1,000 rows, if we're using from 1 to 700 for test training and the remaining 701 to 1,000 for uh, testing, we're using the first 700 for training and the remaining 300 for testing. The question arises that the if we're not randomizing the data, will that be an effect? For let's say if we used the first 200 for testing and the remaining 700 for training, would we get a better accuracy? These kind of questions arise. This is where k-fold cross validation comes in. What k-fold cross validation does is it divides the data into multiple segments. Let's say if you have 1,000 rows of data, it'll be divided into the k is an arbitrary value. So if you're using like let's say four-fold cross validation, your data will be divided into four segments. So if you're dividing 1,000 divided by four, that should be 250 for each. So among the 250, it will be random. Um, so you can use let's say the first 250 for testing and the remaining 750 for training, and the next time it'll be random again. So the next time it can be like the third 250 will be used for testing, and the first, second, and the fourth will be used for training. So it's the data is segmented into multiple. It's segmented into multiple portions, and it will be randomly used to check the validation. That's k-fold cross validation. And finally, there's something called leave-out cross validation. Now, this this is the most. It says it's quite accurate. The thing about leave-out cross validation is you leave out one particular sample. You're not segmenting the data. You're randomizing everything, and then let's say in the first simulation you're using let's say the 999 data to calculate to train your model. So the first row you're using that to test your model, and in the second simulation you're using the first row as training, and you're leaving out the second row as testing, and the remaining from 3 to 1,000 you'll be using that for training as well. So what I'm trying to say is, in the first simulation, the first row should be used for testing, and the remaining should be used for training. Second row should be used for testing, and the remaining will be used for training. So in the third row, in the third simulation, the third row will be used for testing, and the remaining should be used for training. So The thing is that will give you a much accurate result, but it can be quite expensive because that's very time consuming. You have to do this for 1,000 rows of data if you have, and 1,000 rows is actually a very small data set. So cross validation, leave one out. Cross validation means you have to just leave one out and use the remaining for training, and the one you left out, use that single row for testing, and do this for each of all the data. So the good thing is you might get a very good accuracy if you do that because you're using a lot of data to train, but that is very time consuming. It's very expensive. Debug consolidation. All right. So that's pretty much it for this lecture. In this lecture, we talked about decision trees. We talked about induction learning, supervised learning, unsupervised learning, the differences between classification and regression. Then we saw different decision tree examples. Then we saw how we can create our own decision trees using entropy and information gain. Then we did some examples of calculating the information gain. And then we came to the conclusion that sometimes that might not give us an unbiased data decision tree. So we should go for gain ratio instead of the actual information gain value. So we also saw how we could calculate the gain ratio by calculating the split info. And then finally, we saw that some how to determine our model quality, and then we talked about cross validation. So that's pretty much it. That's pretty much all we wanted to teach you for this lecture of learning from examples. So any questions or any confusions? You didn't understand anything? You can ask now. All right. So if you do come across any questions later on, when you're actually practicing the slides and doing it on your own, make sure to reach out to me if you do have any, if you do come across any questions. So on the next class, I think we'll be starting probability. And if I'm, if my calculations are correct, we only have 4 more classes to go. So we still have a lot to cover. And from the next classes, I'll be going a bit fast. I'll be picking up the pace a little more because we have to finish probability and then I think CSP. Okay, so we have to complete probability and then CSP and then adversarial search. And if we get time, we'll look at Bayesian networks as well. I'm not sure if we can cover that. We only have 4 classes. All right, so today's class is officially over. If you have any questions, you can ask, or I think I'll end it here. All right, no questions then. If you do come across any questions later on, make sure to reach out to me. So Thank you guys for coming, and see you next week.